In the last video, I said that antennas radiate and that the electric and magnetic fields decouple from the antenna, and I showed these kind of like lines of closed electric field. But then I mentioned that the dipole antenna in particular radiates in multiple directions, not just in one direction, and that I would explain that more further. And the shape of radiation for all antennas is going to be dependent upon the design of the antenna. So different designs of antennas have different shapes of radiation. And the electromagnetic behavior of all antenna, the most critical thing that we can do to describe the electromagnetic behavior of the antenna is to describe the shape of the radiation pattern, which is also called the antenna patterns. And antenna patterns or radiation patterns are graphical representations of the radiation properties of an antenna, and they're almost always drawn as a function of space coordinates, typically in, as I'm showing here, typically as in three-dimensional space. And these can also be drawn in two-dimensional, and we'll get into that. So what I'm showing here is in the antenna pattern. It's typically connected in or constructed in spherical coordinates, and it's a description of typically the radiated electric, magnetic, or power field at a constant radius. Antennas are, although they're reciprocal devices, so although typically we'll say that this is a radiation pattern, it's also a reception pattern showing which directions antennas will best receive electromagnetic radiation. So if we plot this radiation pattern plot can be a plot of E field intensity or H field intensity, and if that is the plot, we call that a field pattern. And if instead we're plotting the pointing vector, we call that a power pattern. And most often the field and power patterns have been normalized with respect to their maximum value, and then we call them normalized field and normalized power patterns. So typically radiation patterns are normalized power patterns. We will sometimes see normalized E field and normalized H field patterns, but typically what is meant by radiation pattern is a normalized pointing vector. And we'll talk more about that in detail later in the course, but I'm just trying to get a little overview here because a lot of this terminology is new. So the normalized power pattern is often plotted in decibels, which is going to allow us to easily see the difference between areas of what were called relatively high radiation or directions of relatively high power density, and these are called lobes, and areas of relatively low power density, which are called nulls. And an antenna pattern, therefore, is a power pattern typically in dB that's normalized, and it represents the magnitude of the power density in decibels as a function of angular space here. And so here I've just showing an antenna pattern that's been plotted along with the spherical coordinate system so that you can kind of refresh yourself on that. It's the coordinate system most often used in antenna analysis. So here I've taken antenna patterns for a 10-element antenna array. Don't worry if you don't know what a 10-element is. I'm just interested in the power patterns right here. And it's very common that the radiation pattern, the picture I showed on the last slide, is actually just shown in 2 dimensions. Here I've got a field pattern that's plotted using a linear scale. Here for the same antenna, I've got a power pattern plotted using a linear scale. And right here for the same antenna, I'm plotting a power pattern using a logarithmic scale. And some points I just want to note right now are, in the field pattern, I plot out the 0.707 values. This equates to half power point, i.e. the minus 3 dB point from the maximum value right here. In the power pattern, we just go ahead and we mark out the 0.5 points, so that's the minus 3 dB point since this is a power plot, and we can see that we've also plotted the minus 3 dB points on the logarithmic power pattern. And so these are all equate to the same point, right? These points, and these points all equate to the same point. And you can see that the angular separation for all of these equates to 38.64 degrees. I'm actually not sure that I indicated on these, but the angular separation in these plots is 38.64 degrees, and that's called the half power beam width of the pattern. So note that radiation patterns are, can be plotted in terms of the E field or the H field. It's a field pattern, and typically those can be logarithmic or linear, and then the same for power. There.